Okay, Uncertainty Part 2. We're talking about types of data accuracy. And we left off with the subject of inaccuracies of data format, and we'll pick up with positional accuracy. So, positional accuracy. What we're talking about is how far off a set of tested points are from their true positions on a map. And this can be describing both horizontal or vertical positions. So like on a DEM, it could be the position on the map or the elevation. And we can measure it using RMSE, and that's the root mean square error method, which I'm sure you're all very aware of and comfortable with. If not, just so you know what RMSE is, imagine that we have a DEM with interpolated elevations, and interpolated means the values are constructed for cells between points with known values. These DEM values would be considered the predicted values and can be compared to surveyed or known ground measurements, and those would be observed values. So the root mean square error measures how much error there is between those two data sets, the predicted and the observed. Horizontal RMSE compares the difference between locations measured on a map and their true surveyed location, and vertical RMSE describes the interpolated elevations against surveyed or known elevations at the same location. And we're going to go over an example of this in just a minute. Positional accuracy. There are known data standards out there. The USGS has their own mapping standards that state that 90% of points on a map must be within 1/30th of an inch on a 1 to 20,000 scale map or larger or more detailed. And that means that for your standard USGS quad map with a scale of 1 to 24,000, a point on the map should be within 40 feet of the true location of that point, 90% of the time. So what this is telling us is that anytime we see a point on a map, we have its probable location within a certain area. And this goes back to the area error and uncertainty example that we talked about in part 1. So it just means that anytime you see any kind of map, you should be taking all positional error with a grain of salt, right? And the USGS at least tries to quantify it a little bit. When dealing with raster data, there are a lot of aspects to consider when trying to get a feel for the data's certainty. Now, this is an image that displays the same location on 4 different DEMs. There are 4 resolutions and 4 different types of DEM data here. So other than the difference in resolution, which I hope you can pretty clearly see, can you see other differences in the way that this surface has been mapped? So one thing to notice is that this ravine feature on the LiDAR, this is a 2-meter LiDAR data set. This is a 5-meter autocorrelated DEM. Autocorrelated in this instance, this is created from using stereoscopes to look at kind of 3D leaf-on nape imagery. So we're looking at images of the ground through stereo goggles and basically interpolating a surface. But nape imagery is agricultural and is leaf-on aerial images. So there's a ton of vegetation that's actually messing up our ability to see the ground. Most DEMs are bare earth, and these autocorrelated DEMs are created from heavily vegetated aerial images. So that needs to be taken into consideration. This 10-meter NED data is the USGS National Elevation Data Set data. These are quite reliable. And then the 30-meter is also available as an NED product from the USGS, but this version is just a resample of the 10-meter, and I'll talk about that in a second. So like I was saying, the ravine feature on this LiDAR data set pretty much disappears in the autocorrelated data set. But what appears in its place is all of this surface clutter. So is this clutter considered error? Is the lack of it considered error on the LiDAR? Is this uncertainty? It's certainly both. And either way, it definitely needs to be noted and accounted for in some way or addressed. If you pulled the 5-meter autocorrelated DEM for Utah, for example, because you can't get LiDAR for the whole state, and you're thinking, well, high resolution's got to be better than not. You're actually mostly wrong. 5-meter autocorrelated can be a good visualization tool, and we get high levels of resolution precision, but it's quite inaccurate data because of that surface clutter that comes from heavy vegetation. We also lose a lot of ground features that we're going to pick up in other data sets, including the National Elevation data set, which brings that ravine back. We definitely have a loss of resolution, so our precision is lower, but our accuracy is higher than with the autocorrelated DEM. So I think it's important, especially if you're going to be modeling any kind of hydrologic analyses, flow on a DEM like this is going to be pretty messy. You're better off working with a lower resolution data set that's, a lower precision data set that has higher accuracy for stuff like that. Okay, so the USGS NED data is reliable in general, like I said, but you might be interested to know that in large part it's constructed from contours on USGS contour maps. Any uncertainty or error that could be found in those original maps is going to be passed on to the DEM, as well as any errors that might result from the digitizing of those contour lines or interpolating between them. These NED DEMs are improved constantly and quality checked whenever new and or higher resolution data becomes available. So that's helpful. Now the 30 meter, like I said, you can go to the USGS and pull the 30 meter NED data, but the Utah AGRC just went ahead and resampled the 10 meter cell size to a 30 meter cell size. And in doing so, an error resulted. This is going to lead us to a very quick discussion of orthogonality. So this striping that you see, these vertical and horizontal bands, are a systematic error in this data set. It's something that you see pretty often, believe it or not. They're an artifact of an error in resampling. The 10 meter data was resampled to an extent, and they weren't orthogonal with the original raster. And what I'm talking about, orthogonal rasters have to have the exact same grid resolution, so our cell sizes need to be the same, and they have to share the same grid centers, meaning they need to be aligned in the easting and northing directions. This is a little bit different than concurrency, which can also lead to errors, processing errors, and that means that the origin and the extents of the raster data sets need to be the exact same, as well as having to be orthogonal. So that's just something that we can get into later if anyone has any questions about it. So as far as the positional accuracy of rasters go, you might or might not be able to tell from these data sets, whoopsie, here, that there's a slight offset that occurred as a result of this, this resampling. And one student did an analysis in Joe Wheaton's Advanced GIS course here in Logan. The student took those same 4 DEMs and created contours from each one, and then compared the highest contour calculated around a peak. So the star marks a peak location from the LiDAR data set, and this peak was measured at 3,196 meters. The autocorrelated, the 5 meter autocorrelated DEM, that's the contour you see here in pink. And you can see that it's at least overlapping the LiDAR peak. But the peak location on the 5 meter DEM was actually about 6 meters west of the LiDAR peak. So there was a spatial offset. Additionally, the peak value from the autocorrelated DEM was 2 meters lower at 3194 meters. So that's not a huge difference, but there's a little bit of spatial offset. The 10 meter NED data, highest contour, is located here in yellow. The mapped peak location drifted even further to the south and west and is now located about 10 meters away from the LiDAR peak. The peak value read from the 10 meter DEM was 3196, which is the exact same as the LiDAR. So that goes again to the increased accuracy and precision, increased accuracy over the 5 meter data, even though we have a loss of precision. And then there's this big elephant in the room, the 30 meter DEM. You can see that the peak contour has shifted the other direction. In fact, the peak elevation is mapped about 30 to 60 meters east of the LiDAR peak location. That's a huge offset. And the peak cell value is 3188, a difference of about 8 meters, or around 25 feet. Now, this is a good opportunity to talk again about how cell resolution can kind of mute or dampen extreme values, especially peak values. The peak cell, remember, is an average elevation of, in this case, a 900 square meter area around the peak. So there are a lot of lower elevations averaging in to bring that peak cell value down. But the spatial offset just compounds the problem, because now, if you didn't know that and you were pulling a bunch of elevations, you'd have a very biased output data set. So yeah, anyway, that's what I have to say about that. Oh, here are my elevations. So attribute accuracy. This is different than positional. Now we're talking about how real the information is about the location, right? How true they are. Accurate attributes describe geographic features with little variation from the truth, and precise attributes describe the geographic features in great detail. So an example might be whether a Douglas fir stand is described in the attribute table as an aspen stand by mistake. That would be an inaccuracy. Or if it's described simply as a conifer stand, that would be less precise. Or describing it as a Rocky Mountain Douglas fir would be more precise. Hopefully that makes sense. This is a really typical soil map. It's mapped in vector format, which makes a lot of sense because there are a lot of attributes that need to be stored for each feature. So we've got soil type, soil class, descriptions, clay content, moisture. I mean, there are literally thousands of attributes that we might want to store for any given soil area. But soil is obviously a continuous entity, and boundaries between types are going to be more gradual than can be delineated with a line feature. So it's just important to know that attribute error can increase in situations like this near vector boundaries, and that discrete vector data does a fairly poor job of representing gradual change, which would be better handled with continuous data or raster data, but we can only store one cell value at a time. All right, so conceptual accuracy. What we're talking about is using appropriate data for the map's purpose appropriately, and working to present an accurate or logical message. And you can see in this example that the cartographer has failed to symbolize the ratio classes appropriately. This is a map where we're comparing which states tweet more about Ebola than the flu, and a basic ratio was calculated for each state. So values less than 1 represent states in which there were more Ebola tweets than flu tweets, and values greater than 1 mean the state had more flu tweets than Ebola tweets. And by failing to create a neutrally colored class centered on 1, and then using diverging colors for values less than or greater than 1, the cartographer is misleading the map's audience. The map overstates the number of states tweeting more about Ebola. If the values weren't put on this map, the audience wouldn't have any way of evaluating the results that were being presented. For example, if you just took these values off and said more Ebola tweets and more flu tweets, then the audience would have this misrepresentation and wouldn't have any way of knowing. So so this is a good time to quick talk about false precision. False precision is describing when results are more precise than the data or processes that were involved in getting those results. So the results have to agree with the precision of the instrument that collected the data or the processes that were used. And I do talk about this all the time when I'm trying to rein you guys in. When you're giving me a line measurement or something like that that's precise to the millimeter, I just can hardly think of any situations where we're going to have data that precise. Another example would be taking a land cover map that has a 5-kilometer resolution, 5-kilometer cell size. You wouldn't report, for example, that tussock grasses cover an area of like this, where we've got this kind of precision. In addition to raster resolution limiting the precision with which we can report our values, there's uncertainty about the initial mapping. How was this land cover mapped? Was it a manual survey? Was remote sensing used with image classification? What kind of algorithms were used? What's the margin of error on the mapping of the land cover itself? And then there's temporal issues to consider. How old is this data? How current is it? Have there been massive wildfires that have totally changed this map since then? So the reported value needs to align logically with the purpose of the analysis, with your audience and with the estimated uncertainty of the input data. Another example is if you're out collecting GPS data with a commercial handheld that has a stated accuracy of 3 to 5 meters or 10 meters. The data collected is going to have a margin of error of 3 to 5 meters, and therefore distance measurements made from those GPS data should be reported with a 3 to 5 meter margin of error, right? And then there's another funny example that I found on Wikipedia where a tour guide at a museum says a dinosaur skeleton is 100,000,005 years old because an expert told him that it was 100 million years old when he started working there 5 years ago. So we need to be careful when we're kind of mixing two different scales of certainty, right? I mean, that's a great example. So I'm just going to pause here and then we'll continue next with error sources and how to deal with positional error.